welcome back from the midterm exam. I hope you had a nice midterm exam. We have not checked the paper so far. We are working on it. We'll let you know about the result as soon as we have your grades for the midterm. Before midterm, we covered chapter number 1, chapter number 2, and chapter number 3. And now we are going to start chapter number 5, which is the CMOS inverter. Here is the symbol for the CMOS inverter, and as we have already discussed it so many times that the CMOS inverter complementary metal oxide semiconductor does have an NMOS, it does have a PMOS. The PMOS is connected to VDD, and the NMOS is connected to ground. Right. I'm going to need responses from you as well. And then the input,
okay, sir.
right, and the input is connected to the gates of the PMOS and to the gate of the NMOS. And then the output is connected, okay, all right. Here is a question for you. What is the output connected to for the PMOS and for the NMOS?
So again, repeat the question.
What is V out connected to for the PMOS and for the NMOS? Like, we know here is the gate for the PMOS and here is the gate for the NMOS, and the input voltage is connected to the gates of the PMOS and the NMOS. All right, then we have for the PMOS and NMOS, we have individual drain and sources, right? So what is the output connected to over here for the NMOS? Just consider for the NMOS. Is it connected to the drain or to the source? Okay, let me tell you. The output voltage is connected to the drain for the NMOS and to the drain for the PMOS as well. You need to remember that, right? And the ground of the NMOS is connected to the source. All right. And the source of the PMOS is connected to VDD. And there is actually a reason for that. Why is the, for example, let us just consider the example of an NMOS. Why is the ground connected to the source? First of all, mostly the source and the bulk are connected together. They are connected to each other. We have discussed NMOS individually and PMOS individually. And then we have discussed N-type MOSFET. And in N-type MOSFET, you might have observed that the source and substrates are connected together. Then do you remember that for an NMOS, the substrate is connected to ground? And do you remember the reason for that?
No, sir.
There was a question in your exam as well that why. Okay, so the reason is that we need to reverse bias the drain and the substrate so that the current does not leak from the drain to the substrate. If you apply positive voltage to the drain and apply a negative voltage to the substrate for an NMOS, then it is reverse bias, because what is the substrate for an NMOS? What is the bulk for an NMOS? Is it going to be P-type or N-type? For an NMOS, the channel is N-type, the drain and the sources are N-types, but what is the substrate made up of? It's going to be P-type, right? For an NMOS, the substrate is P-type. All right. If the substrate is P-type, the drain is N-type, then what voltage do you need to apply to the substrate to make it reverse bias? Negative voltage are connected to ground. And by reverse biasing the drain to the bulk, you don't allow current to flow from the drain to the bulk or from the drain to the substrate. The goal is for the current to let the current flow from drain to source via the channel, but not from the drain to the bulk. All right. So that's why we would connect the source of the NMOS to ground. And for the same
Right.
reason, for the same reason, we are going to connect the source. So here is the source of the PMOS transistor. We would connect the source of the PMOS transistor to VDD to make it reverse bias so that the current does not flow from drain to the substrate. The current flows from drain to
Okay.
source via the channel. So we already discussed it. And then another key point is that in CMOS, you under similar conditions, you might like similar amount of currents to flow through the PMOS and through the NMOS transistors. But we previously discussed, and you might remember the mobility videos for N-type silicon and for P-type silicon. Do you remember the mobility for N-type and P-type silicon? For N-type silicon, the mobility is approximately 1500 centimeter square per volt second. For P-type silicon, what is the value? It's approximately 450 centimeter square per volt second. And then the conductivity is directly proportional to mobility. Conductivity is equal to charge times mobility times carrier concentration. So that means if the mobility of the P-type silicon is lower as compared to the mobility of the N-type silicon, it means that for same carrier concentration and for same widths, the current across the P-type transistor or the PMOS is going to be lower as compared to the current across the NMOS. So for that reason, what we do is we make the PMOS transistors wider, 2 times or 3 times wider. Mostly it's 2 times wider for different reasons that we are going to dive deeper into. But we keep the channel length constant for the PMOS transistor and also for the NMOS transistor. But the width of the PMOS transistor is double so that to counter for the mobility effect, because of the lower mobility of the PMOS, it's going to drive lower current. So to counter for that, we increase the width of the PMOS so that we can have balanced currents across both the PMOS and the NMOS transistors. And we are going to discuss in detail later. And you might remember the performance, the quality metrics for VLSI design. So this chapter mostly focuses on inverter and its quality metrics. Why inverter? Once again, going back to the previous slides. Inverter is the nucleus. It's the focus of all digital designs. And then if you understand inverters, you can extend it to NAND gates, you can extend it to NOR gates, and you can extend it to so many other modules and systems as well. Like you're going to learn later that NAND gates, you can also make NAND gates and a combination of NOR gates via inverters and so on. Everything will have the PMOS transistors and the NMOS transistors. So if you understand the operation and the performance metrics of inverters, you pretty much understand NAND gates and NOR gates and complex circuits as well. Right. So this chapter mostly focuses on analyzing the performance or the quality metrics of VLSI design for inverters. The quality metrics are cost, reliability, performance, and energy or power dissipation. We already discussed cost, the non-recurrent engineering cost and the recurrent engineering cost, and the cost mostly is based on the complexity and area of the transistors. Reliability determines the robustness or the repeatability of the of your circuits, of your inverters, and it's mostly expressed by static. What is static? Static means the steady state behavior of the inverters. Speed is determined by the dynamic behavior or the transient response of your inverters. I mean, it does depend on the capacitances of the individual transistors in the inverter. Inverter does have a PMOS transistor, it has NMOS transistor, and we already discussed the capacitances for these type of transistors. Do you remember any of the capacitances? I know that sometimes after your exam you just clear your cache, but do you remember the capacitances? What kind of capacitances we have for transistors?
सर कट ऑफ रीजन की कैपेसिटेंस
Yeah, I mean the kind of capacitance are the gate to bulk or gate to channel capacitances, the diffusion capacitances, the
ओवरलैपिंग
overlap capacitances, right? So
यस सर
because of these capacitances, depending on the input voltage, it's going to take time to charge or discharge these capacitances, and that determines the dynamic or transient response, or how long does it take for the capacitor to fully charge or discharge. And the charging, this dynamic or transient response will determine the speed or delay of the inverter. And then energy and power dissipation. Once again, I'm copying these slides from chapter number 1. We already discussed the types of cost for integrated circuits. There are non-recurrent or engineering cost, including fixed cost, and the examples are fab, design effort, mask generation, equipment, etc. And then there are recurrent engineering costs, which are proportional to volume. Examples are materials processing, assembly, packaging, and testing, etc. Mostly we are going to focus on reliability and performance of the inverters in this chapter, and energy and power dissipation to some extent as well. I still have to decide some of the contents with Dr. Suhail Saab. But what is reliability? Reliability means to perform a repeatable function, to perform the function that the inverter is designed for. Now, deviations may occur from its designed function because of the variations in the manufacturing process. Like, we remember the fabrication process. It does have lithography, ion implantation, deposition of silicon dioxide, deposition of silicon nitride, and then removing the silicon nitride sacrificial layers and other layers from time to time. So a slight variation in the manufacturing process in ion implantation or in any of the other steps might affect the reliability of that inverter or of that circuit a lot. And then the second factor which can affect the reliability of inverters or other integrated circuits is noise, which are unwanted variations of voltages and currents at the logic nodes. There could be multiple sources of noises. Inductive coupling, as we already discussed, that on printed circuit boards we have loops of metallic tracks, and these loops act just like an inductor. So if the design is not robust, if it is not designed well, keeping in mind all the factors related to inductances, a signal from one loop might couple to a signal into the other loop where we have our inverter circuit. Or if two wires are running together, it's just like a capacitor. We have two metals, and then wherever we don't have metal on our integrated circuit, we deposit silicon dioxide to prevent unwanted particles on our integrated circuits. So if you have two metal wires with an insulator between them, it's going to act just like a capacitor. So there could be coupling of capacitive of signals because of these capacitance effect as well. And also noise could also come from the power supply from the source or from the ground, which might affect the reliability of the inverter. We discussed the voltage transfer characteristic of an ideal inverter.
एक्सक्यूज मी सर, सॉरी टू डिस्टर्ब यू। मैं ये कहना चाहती कि अगर हम इसको रिकॉर्ड कर लें तो जो स्टूडेंट अभी नहीं अवेलेबल उनके लिए अपलोड कर देंगे। ये आई गेस रिकॉर्ड नहीं हो रहा है।
I'm recording it.
ठीक है सर, थैंक यू।
I'm recording it.
थैंक यू।
No problem. Okay. We discussed the voltage transfer characteristics of an inverter. And let's go to the next slide. In fact, voltage transfer characteristics are, we plot the output voltage versus the input voltage, and then for an ideal gate, for an ideal inverter, what are the qualities of the ideal inverter? We discussed it already, and it's given in this slide as well. It's going to have infinite gain in the transition region, or zero gain,
Yes,
zero gain over here and zero gain over here. The threshold voltage is located in the middle of the logic swing over here, and the high
yes, sir.
and the high and low noise margins are equal to half the
Half of VDD.
logic swing, VDD divided by 2.
Yes, sir.
But in reality, the real voltage transfer characteristics do not have these properties. We can get them closer to the ideal, but we cannot really get the ideal voltage transfer characteristics for an inverter. So here are the real voltage transfer characteristics, plotting V out versus Vn. In real voltage transfer characteristics, the gain is not exactly zero over here or over here, and also there is going to be a finite gain in the transition region. Then the points where our slope is -1, we draw a line onto the x-axis, which is the input voltage, and draw a line over here as well, and we call it our input low voltage. So from 0 point to VIL is our logic 0 for the input, and then from VIH to VDD, somewhere over here we are going to have our VDD. From VIH to VDD, we will have logic, we consider it logic 1 or logic high at the input voltage. And then noise margins I already discussed. Noise margin high is the difference between VOH minus VIH, and noise margin low is the difference between VIL and VOL. And then I wanted to draw the more extensive plot over here, but we don't have access to the whiteboard right now. But anyhow, that other figure also helps a lot. We previously discussed this with the help of an example as well, how to determine the noise margins, and how to calculate the voltage swing. It's not given, but can anybody tell me what is the voltage swing for this plot? Or based on these parameters, can anybody tell me what is the voltage swing? So VOL is 0.45. Let's go directly to the answers. So here is our VOH. It's approximately 3.5 volts, and our VOL is 0.45. Voltage swing is the difference between VOH and VOL, which becomes 3.05. Then how about the noise margin high and noise margin low? Let's go back to the previous slide. VOH minus VIH, the difference between these two voltages, it becomes 1.15. And noise margin low, difference between VIL and VOL, VIL minus VOL becomes 0.21. It's actually a gate from 1970s, an NMOS inverter, and looking at its voltage swing, the voltage swing is not good. We want voltage swing from rail to rail, from 5 volts to 0 volts. So the voltage swing is not good. The threshold voltage is not in the middle of the logic swing, and also the noise margin high and low are not equal to half the logic swing. So it's not a good inverter, but anyhow, the example is given just to let you know how to calculate these parameters. Let's try to relearn defining some terminologies. Fan in and fan out. What is fan out? Fan out is the number of logic gates connected to the output of an inverter or a gate. And what is fan in? The number of inputs to a gate. So it's pretty simple. Talking about performance, and in performance the key metric is delay. We have our logic module. In this case we have an inverter. We apply an input and we are going to receive an output, but there is going to be it's going to take a certain amount of time for the gate to give its output. And where does the delay come from? Once again, we have an inverter. The inverter is composed of PMOS and NMOS transistors. And these gates are going to have delay. The delay comes from the capacitances, right? Because it's going to take time for the capacitances to charge and discharge. For example, here we have our input signal versus time. The input signal is transitioning from low to high. Then here we have our output signal plotted versus time. If the input is low, the output is going to be, for an inverter, if the input is low, the output is going to be Can anybody respond, please?
सर इनपुट अगर लो होगी तो आउटपुट हाई होगी हमारे पास.
Yes, so here is our input voltage. Here is the voltage at the input of the inverter. If the input is low, the output is going to be high, and we can see it over here. But then at this point the input starts transitioning from low to high. So if there wasn't any delay, the output would have started transitioning right away from high to low. But because of these capacitances of the individual NMOS and PMOS transistors, it's going to take certain amount of time for the output voltage to respond. So it takes a certain amount of time, and after that it starts transitioning from high to low. And then how do you measure these the delay? You measure the delay by measuring the transition from at the 50% points. Here is the 50% point of the input, and here is the 50% point of the output waveform. So you measure the difference, and we call it the propagation delay from high to low transition for the output. And then you also measure the delay at when once again this waveform starts transitioning, the input waveform starts transitioning from high to low. So your output waveform is going to transition from low to high, and we call and this propagation delay is called propagation delay low to high. So you just take the average of propagation delay low to high plus propagation delay high to low and divide it by 2, take the average to calculate the total propagation delay for this logic gate. How do you model propagation delay? We can model propagation delay with the help of an RC network. So if here is our input voltage, we can model it with the help of a resistor and with the help of a capacitor. We already discussed where does the capacitor come from. The capacitor comes from the individual NMOS and PMOS transistors because of their diffusion capacitances, overlap capacitances, gate to bulk or gate to channel capacitances. Does anybody have the idea where the resistance come from? Like we discussed that we can model propagation delay with the help of an RC network. Now we know where the capacitance comes from, but do you know where the resistance come from? Well, that's fine. We can talk about it in the upcoming slides. But the resistance also comes from these individual transistors, and I'm going to tell you how, and going to tell you why. You can model it with the help of a simple RC network. We previously discussed it. Time to reach the 50% point is 0.69 times tau. What is tau? Tau is the product of the resistance and the capacitance of the transistor.
Okay.
And then time to reach the 90% point, 2.2 times tau. And we derived these previously as well. Power and energy dissipation. Going to skip a couple of slides, and then energy in CMOS. Okay. So here is if our input voltage, I mean, it's actually not the input voltage to the power supply. You can consider it VDD. Now, once again, it's sometimes it becomes difficult to clarify concepts when we don't have the whiteboard. But anyhow, I previously discussed it that consider the example when the input is low. All right. If the input is low, and then let me try to see if we have this capacitor model somewhere. We don't have it over here, but yeah, let's go back to slide number 2 and just assume we have a capacitor over here connected at Vout between Vout and ground. So if the input is low, what happens? Which of the two transistors is conducting? If the input is low, is the PMOS going to be on, or is the NMOS going to be on? If the input is low, the PMOS is going to be conducting, right? So if the PMOS is conducting now, and the NMOS is going to be in cutoff. If the PMOS is conducting,
Yes,
if the PMOS is conducting, and we have a capacitor over here, then we have this path from VDD. The PMOS is conducting, and then we have
Vout.
Vout, but we have a virtual capacitor in this part which I have not drawn, but we are going to have a capacitor over here. So that means that our capacitor is charging from VDD via this path. Then what happens if the input is high? Which of the transistors is going to be conducting?
NMOS.
The NMOS is going to be conducting, and the PMOS would be turned off.
Cut off.
And cut off. Alright, so this capacitor is going to start discharging via, we have a virtual capacitor over here, is going to start discharging via the NMOS. Right, now let's go forward once again to to over here. So there is a resistance in this path as well. Let me go forward to here are the let us look at slide number 24. Here are the equations for MOSFET in different modes of operation: in cutoff, in linear region, and in saturation. And then we have the curves for the MOSFET as well. Now, as you can see, as we increase VDS, ID is also increasing in the linear region, and then there is a saturation region as well. So if you just consider an NMOS, if you increase VG beyond the threshold point, it's going to increase the current across the channel as well, right? So you have a voltage and you have current. If you increase current, if you increase voltage, the current is increasing. So that means that this channel does have a certain amount of the resistance as well. And our resistance from this model of RC network comes from the channel. The capacitor comes from different sources, which we already discussed in chapter number 3, but the resistance comes from the channel. The total energy delivered by the source, we previously derived it, is equal to CV square. But how much energy is stored in this capacitor? So CV square is delivered by the source, but how much energy is stored in this capacitor is equal to CV square divided by 2. And we discussed it previously, but let me ask this question once again. The source is supplying CV square amount of energy, but the capacitor is charging CV square divided by 2. So it's storing half of the energy supplied by the source. Where does the rest of the half of energy go into?
सर वो रेजिस्टर जो है वो अपने अंदर जो है डिसिपेट कर लेगा.
Yes, that's exactly.
वो भी तो लेगा ना कुछ एनर्जी.
James, that's a good answer. So the rest of the energy is going to be dissipated in the resistor, and it's going to be lost, dissipated in the form of heat. So the transistor can be modeled as a switch. If the threshold, if the gate to source voltage, if the input voltage is less than the threshold voltage, the transistor is going to be in. If VGS is less than threshold voltage, off, okay, it's going to be in cutoff because the channel is not formed. So it's going to be in cutoff. But if VGS is greater than VT, it's going to start conducting. So the switch would be turned on, and then it will have a certain on resistance as well, because the channel, as we increase or decrease the voltages above the threshold voltage, the current is also going to start increase or decreasing. So that means the channel does have a certain amount of resistance as well. So you can model the transistor with the help of a switch as well. And we already talked about it, but anyhow, the transistor does have different modes of operation. The first mode of operation we discussed is accumulation, but it's not significant from the point of view of these slides. Do you remember the condition for accumulation, by the way? For if this is an so this is a MOS, and the substrate is P-type. In terms of MOSFET, we are talking about N-type MOSFET. But do you remember the condition for accumulation? What is the condition for accumulation mode of operation? We don't need it over here, but still. If the substrate is P-type, accumulation mode means we try to accumulate.
हम उसके लिए अप्लाई करते हैं नेगेटिव वोल्टेज.
Yes, negative voltage अगर apply करें, if we apply negative voltage, it's going to attract holes from the substrate towards the surface.
Yes, sir.
Then
substrate. Yes, sir.
In depletion mode of operation, we apply a positive voltage to attract but the voltage is small. So what happens is initially it's going to push away holes from the surface, and it's going to act
रिपेल
just like
करेगा सर
and it's going to act just like an intrinsic material. And we can see that in the energy band diagram as well, where at the surface the intrinsic energy level coincides or concurs with the Fermi energy level, which means at the surface this acts just like an intrinsic material, but the bulk properties are not going to change. And here is a MOSFET in a depletion mode operation. Inversion mode operation. If we apply a large positive voltage, it's going to start attracting electrons from the bulk p-type material as well, and it's going to form an inversion layer of electrons, and we can see it from the energy band diagram as well. Forms a channel. You keep increasing the voltage in the linear mode of operation. The channel, the carrier density in the channel is going to increase, and the current is going to increase. But then by increasing this voltage above a certain level, and then we are going to apply VDS as well. So there is going to be a saturation region as well for drain to source voltage. The inversion mode operation for a MOSFET. And here are different modes of operation. And you got to remember these conditions. I know that for your exam you were allowed to list them down, but basically what happens in cutoff, your gate to source voltage VGS minus VT is less than 0, which means VGS is less than,
सर क्योंकि हमारा जो होगा वो ऑन नहीं होगा तो आईडी जो होगा वो 0 होगा, करंट नहीं होगा.
Yes, if the gate to source voltage is less than the threshold voltage, it means we don't have any channel and our current is going to be 0. But you got to remember this condition, VGS minus VT is less than 0, or it means that VGS is less than VT.
Yes, sir.
In linear mode of operation, now your VGS or the gate to source voltage is greater than VT. So that is the first condition. And the second condition is VGS minus VT is also greater than VDS. And then here is our current equation. Now in the current equation, as you can see that your current is proportional to a lot of other parameters, but it's also proportional to W divided by L. It's significant because, and similarly for the saturation region, once again, the first condition is our gate to source voltage is greater than VT, and the second condition is VGS minus VT is less than VDS. So this is another condition, but once again this ID, the drain current, is proportional to W divided by L. So if we, for the PMOS and NMOS transistors, if we keep channel length constant because it defines the technology node, technology parameter. We say this is 5 nanometers or 3 nanometers or 7 nanometers technology. We say it on the basis of the channel length. So we keep the channel length constant for both PMOS and NMOS transistors. But since the mobility of p-type silicon is lower as compared to the mobility of or the mobility of holes in silicon is lower as compared to the mobility of electrons in silicon. So that's why we say if we keep W constant for both PMOS and NMOS, if we keep them the same for PMOS and NMOS, then because of the low hole mobility, the PMOS will have lower current as compared to the NMOS. And we would like to have balanced currents for the PMOS and NMOS transistors. So that's why we slightly increase the width to length ratio, or the width for the PMOS as compared to the NMOS, and for both cases, so that the currents are balanced out for the PMOS and NMOS transistors.
Okay, sir.
And once again, these concepts are crucial for discussions that are going to happen later in the next coming lectures. But you got to remember that our ID, the drain current, is proportional to W divided by L, or especially to W, and that's why we play with the W parameter for the PMOS and NMOS transistors to balance the currents for these two kinds of transistors for the inverter. Here are the ID versus VDS curves for the NMOS transistors. Nothing significant here other than we have resistive regions and we have saturation regions, and the equations are already discussed. Switch models for the CMOS inverter. Here is our CMOS inverter. Pretty much similar to what we already discussed in the previous slides. If the model for high input, if the input is high, which of these two transistors is going to conduct? Which one of these is going to be on if the input is high? So you got to remember this. If the input is high, the NMOS transistor is going to be on. If the input is low, the PMOS transistor is going to be conducting. From this point onwards, you have to memorize this point. If the input is high, which of the transistor is going to be conducting? The NMOS transistor is going to be conducting if the input is high. If the input is low,
Yes, sir.
if the input is low, the PMOS transistor is going to be conducting.
Conductor.
All right, so we can model it with the help of a switch as well. Then for high input, the input is this NMOS is going to be conducting. So our Vout is connected to ground. This is in cutoff.
And
Vout is
yes,
connected
sir.
to ground, but we already discussed that these transistors, because of the current flowing through the channel, and that channel current is proportional to the voltage, it's going to have a certain amount of resistance as well. So Vout is going to be connected to ground, but via a certain resistance of the end of the channel, of the end channel. All right, Vout is connected to ground
Yes, sir.
via a certain amount of resistance. Now, if the input is low, Vn is equal to 0, model for low input. If the input is low, this transistor, the NMOS, or the pull down transistor is going to be in cutoff, and the pull up transistor is going to conduct. So this transistor is on. So Vout is connected to VDD, but via the channel resistance, through a certain resistance, and we call this resistance as RP. Vout connected to VDD via RP. So this is the model for low input for the CMOS inverter. And these transistors will have certain widths. Wn is the width of the N-type transistor, Wp is the width of the PMOS transistor, and generally for inverters, Wp is equal to beta times Wn, 2 times or 3 times Wn, so that to balance out for currents due to the difference of mobilities in holes and electrons for silicon based, and also, I mean, the difference is, so holes have lower mobility for silicon. For silicon, I think it's 450 centimeters square per volt second. For silicon, electrons have mobility of 1500 centimeters square per volt second. But generally for other materials as well, the mobility of holes is much lower as compared to the mobility of electrons. I think for gallium arsenide, the mobility of electrons is 8500 centimeters square per volt second for electrons, but for holes, mobility is approximately 400 centimeters square per volt second for gallium arsenide. Similarly for germanium, I think the mobility of electrons is 3900, but the mobility of holes for germanium is 1900. So it's not just the case for silicon, it's the case for other materials as well. ID versus VDS curves for an NMOS, for a PMOS. I want to start slide number 27 in the next lecture, and we are going to cover just a few slides in the next lecture, slide number 27 to slide number 36, but it's these are time demanding. Conceptually, we need to spend a lot of time on them to learn the concepts of these slides. So that concludes the lecture for today. Do you have any questions from the slides that we already discussed? Right. If not, we also need to decide time for another lecture for a makeup class for this week, because we already missed one lecture and we need to be on time in terms of lectures. We have to cover a lot of material. So are you all available tomorrow for another lecture? And if yes, what time?
यस सर, हम डिस्कस कर लेंगे क्लास में जो जो किस टाइम पे अवेलेबल है तो उस टाइम पे रख लें क्लास.
ठीक है. चलें, आप इस तरह से कर लें, आप आपस में डिस्कस कर लें और डिसाइड अ टाइम फॉर टुमारो और ग्रुप चैट में फिर डिस्कस कर लें, पोस्ट कर लें. ठीक है.
ओके सर.
Right. That concludes the lecture for today. Take care. Allah Hafiz.
ओके सर, अल्लाह हाफिज.